Hey guys, today we are going to be looking at continuity. We're going to define what it means for a function to be continuous and then talk about the different types of discontinuities that can occur and then how to identify those and justify those as well. So that's where we're starting off today. So continuity has to deal specifically with the idea of limits. We learned about different types of discontinuities previously in pre-calculus, but just how to recognize them from a graph. Now we're actually going to learn why they exist. So first and foremost, we would say a function f is continuous at a number a if the limit of that function as x approaches a actually equals what that function value is at a. All right. This definition requires three things to be true, and this is going to provide a sort of checklist for you to go through whenever you need to decide whether a function is continuous or not. So first of all, f of a has to exist. So that's the very first thing that you want to check for functions is, can you just plug in the number that you care about and actually get a value out? Because if you don't, then automatically your function fails this first step and would be discontinuous. So this is the very first thing you check. Then you have to check and see if the limit exists. And when we do that, sometimes you might have to check your left and right hand limits. Okay. And then last but not least, once you know that they both exist, you have to see if they actually equal each other. So if those three things are true and you check them in that order, then you would say your function is continuous at that number, okay? If a function does not meet any of these conditions, so if it fails the first one, the second one, or the third one, or more than one of them, we would say that the function f is discontinuous at a, or you could say f has a discontinuity at a. So either way of saying it would be 100% correct. All right, let's go ahead and we're going to look at this example down here. So this example has a couple of discontinuities on it, and so we're just going to remind ourselves what those are. So first of all, this discontinuity here is a removable discontinuity. So you can just kind of write yourself a note. Removable. It has a hole in the graph. That's often how it's described. And then this one down here is actually also a removable discontinuity. So removable on your graph looks like you're going along on the function and somebody literally picked a point out of your graph, and they can either put it somewhere else on the coordinate plane or they can just remove it altogether, like in this example here. All right. Let's also look at this type of discontinuity. So when your graph seems to approach a certain value and then jumps, that's called a, it's funny, a jump discontinuity. So when your graph looks like it stops in one place and then picks up somewhere else. And then the last one is actually important that we draw this line as well, is whenever you have a vertical asymptote and your graph approaches that asymptote forever, this is what's known as an infinite discontinuity. Okay, and it's recognized by a vertical asymptote. Okay. So those are graphically what happens. Now let's talk about the justification for them. And so I'm going to kind of go back and forth between this graph and the next example because it's on the next page. All right, so first of all, we're going to talk about why the function is discontinuous at x equals -1. So if I look at x equals -1, we would say our function is discontinuous, and you have to check your three steps that are above, right? So first of all, do I actually have a point at -1? I do. So it technically passes the first test, or the first step. Do I have a limit at x equals -1? Well, I do, because as I approach from the left and as I approach from the right, my limit exists and is 1. So my point is actually at 2, my limit is 1. So the reason that I actually have a discontinuity on this graph is because my limit does not equal what my actual point is. So that would be the reasoning behind this one, because, whoops, the limit of my function as x approaches -1 does not actually equal the point at -1. Okay. Let's look at 0. So why do I have a discontinuity here? Excuse me. So I do actually have a point here, right? I have f of 0 would be considered 1. And then when I do my limit here, you have to check from the left and the right-hand side. And on this first one, from the left, it was +1. From the right, it approached 1, so that limit existed. The reason for the jump discontinuity here is because my left-hand limit is 2 and my right-hand limit is 1. And so that would be the reason this would fail the second step. My general limit doesn't exist because my left and right-hand limits didn't exist. So I would say that my limit of this function as x approaches 0 does not exist. And then if you want to give some more description for that, because my left-hand limit does not equal my right-hand limit. So that could be the other reason for a discontinuity. If we go ahead and we look at 2, x equals 2, the discontinuity that's there, well, right off the bat, this actually just fails the first step. The first step is, do you actually have a point? Is f of 2 defined anywhere on here? And we can see that there is no point actually on f of 2. So this just right away fails the first checklist piece. So we'd say because f of 2 is undefined. And then last but not least, the function is discontinuous at x equals 5. That would be for exactly the same reason, right? I don't actually have a point anywhere at 5. I have an infinite asymptote. Also, you could say that this limit doesn't exist, right? The limit technically here from the left-hand side would equal infinity, but infinity, remember, is just a more specific version of saying does not exist. So we could say that f of 5 is undefined. That would be a reason. Or you could say the reason is that your left-hand limit as you approach 5 from the left-hand side is infinity. Okay, so those would just be 2 reasons that this would be discontinuous. You can go ahead and list your 3 types of discontinuities down here again, right? So there's a removable, which would result in a hole in your graph. There is a jump discontinuity, which results in a jump, and then there is an infinite discontinuity, which results in a vertical asymptote. Okay. All right, so now we looked at how to look at it from a graph, so now we're going to do it with actual equations as well. So it says determine if each function is continuous at the indicated x value. So we're looking to see if your function passes the 3 steps. So first of all, is f of 1 defined? Does the limit exist? And then do they equal each other? This is all you have to show when you're trying to show that something's continuous. So first of all, we have to say, is f of 1 defined? So I'm just over here going to go ahead and just plug 1 into my equation and see what I get. Well, if I plug 1 in there, I get 2. Okay, so check, yes, defined. Then the next step is, does your limit exist? So limit of f of x as x approaches 1. Now we know the fastest way to check a limit, or the first thing you should always do, is just to plug it in. So if I go ahead and plug it in, I do also get 2. Check. And then last but not least, does my limit actually equal what my function is? Yes, it does. So we would say, yes, continuous at this value. All right, and now let's go ahead and try another example. All right, so first and foremost, we have to see, is g of 1 defined? So if I actually just go and I plug g of 1 in, I get 1 squared minus 1 over 1 minus 1, and I get 0 over 0, which is undefined. So automatically fails, right? for actually just plugging values in, we don't try to factor, we don't try to do anything. When you're literally just plugging values into a function, you just have to see what your answer is automatically. The only time that we would then move past this is if we're trying to find the limit. But here we're not trying to do that. We're literally just plugging 1 in and seeing what we get. And because automatically g of 1 is not defined, then we would say that this is not continuous, or it has a discontinuity at x equals 1. Okay, let's go ahead. I think I got 3 more. Yeah, beautiful. All right, in this next one is L of -2 defined, right? Because here's my function. So again, I'm just going to go ahead and I'm just going to plug in a negative, find L of -2. So then I have -2 plus 2, which gives me 1 over 0, automatically undefined. Fail. Discontinuous. Better be consistent. All right, in example 5, we're going to do the same thing. Now this is a piecewise function, so we just have to pay attention to where we're putting things or what we're doing for finding limits. So first of all, is k of 0 actually defined? In a piecewise function, you have to look at when you're just plugging a number into your piecewise function, you need to plug it in where you could actually equal 0. So we're going to use the bottom piece because that's where I could actually equal 0. So k of 0 is 0 squared minus 1, which is -1. Okay, so k of 0 is defined. That's good to go. Next, I'm going to see if my limit exists. And automatically with a piecewise function, we should be thinking left-hand limits and right-hand limits. So let's see, my left-hand limit would be if I plugged 0 into the top function, because I'd be approaching 0 from values less than 0. So if I plug 0 in there, I get 2. And then my right-hand limit would be if I plugged it into the bottom piece of my piecewise function, because that would be for values greater than 0, but very close to 0. So if I plug 0 in there, I get -1. And so technically, my limit doesn't exist, right? My general limit doesn't exist because my left-hand limits and my right-hand limits are not the same. So this one is also discontinuous at x equals 0. All right, last but not least, we're going to do this last example and then we'll take a break from our notes. Is p of 3 defined? So if I actually plug 3 into this function, where can I actually equal 3? Well, it'd be at this bottom set. So p of 3, when I actually plug 3 in, I get 4. So that's defined. Then does my limit exist? So let's do my left-hand limit and my right-hand limit. 3 from the left-hand side. So if I'm plugging in things close to 3 but a little bit less than 3, I'll use the top part, which would be 3 plus 2, which would be 5. And then actually, if I'm paying attention to this, right, if I'm plugging in things that are a little close to 3, but also from the right-hand side, which would be my right-hand limit, I'm still going to be using the top part. That's the perk of having a not equals to symbol as a breakup in your piecewise function, because this basically says you're just going to use this piece for everything that's around 3. So for things that are greater than 3 and things that are less than 3. So my general limit does exist. It's 5 because my left-hand limit and right-hand limit match. But then now you have to check the last step. Does your limit actually equal what your value was when you plugged in 3? Well, my limit is 5 and my actual value is 4, so this fails the last step. So this one is a discontinuous. Whoops. At x equals 3. All right. Let me know if you have questions.